Well, good afternoon. Welcome to the Department of Chemistry, welcome to the Cambridge Science Festival, and welcome to this lecture on rocket science. Now, every rocket that has ever flown, whether it's a small firework rocket or whether it's a giant rocket that's carrying people to the moon, every rocket is based on one simple principle. So I thought I'd begin this lecture by demonstrating that principle. So this is a beautiful reproduction in miniature of a Napoleonic cannon, but it's a working model, and it's actually capable of firing a live round, a half-inch diameter lead cannonball. Today we won't fire a live round, but I'm going to fire a blank round, and when we do, I want you to observe what happens to the cannon. Now, the cannon is really just a tube that's closed at this end and open at this end. This is called the muzzle. And there's a small hole called the touch hole that we use to transmit fire to the main charge. So I'm going to begin by taking a piece of slow-burning fuse and placing that in the touch hole. And then we're going to charge this with gunpowder. So the gunpowder is in this nice powder horn. The way this works is I put my finger over the brass nozzle, I press the valve and tip it upside down, and powder trickles into that brass spout. So we're measuring a precise quantity of gunpowder. And I release the valve and turn it right way up again, and we have a measured quantity of gunpowder in the spout. So I'll place that into the barrel of the cannon. And I thought, since this is Science Week, we'll use a double dose. Well, here's a double dose of gunpowder going into the cannon. So that's the gunpowder in the barrel. I'll put this safely out of the way. Now, to keep the gunpowder in the barrel and keep it up against the fuse, we're going to use a little bit of wadding. So this is some fireproof wadding, which I'm going to put into the muzzle of the cannon, and then use this ramrod to pack the wadding and the gunpowder tight up against the fuse. Now, at this point, we would put our cannonball in. We're not going to do that today, so instead we'll simulate that by using a bit more wadding. So I'm going to put some more wadding into the barrel, and again, just pack that down. And then finally, to stop the ball rolling out, as it were, we'd use a bit more wadding, so why not? Let's do a bit more wadding. It is the Science Festival, after all. Okay, so we've got this wadding nicely packed down. Our cannon will be loaded, and it's now ready to fire. So I'm going to light the fuse. From where I'm standing, it's quite noisy, so I'm going to be covering my ears. If you're near the front, you may wish to do the same. When the fuse burns down and the cannon fires, I want you to look carefully what happens to the cannon. So here we go. Okay, so as you saw, the cannon shot backwards. We call that recoil. And this is a very basic principle of physics. It's the idea of conservation of momentum. So when the cannon fired, hot gases and pieces of wadding were shot out of the barrel at great speed in this direction. So those pieces of material had a lot of momentum in this direction, but the total amount of momentum in the world can't change. And so the cannon acquired some momentum in the opposite direction. So this is the basic principle of the rocket. By firing gases very fast in one direction, we create a force in the opposite direction. Now, this cannon is very nice, but of course the force was created sort of all at once. We just had an explosion. If we want to build a rocket, what we need is a nice steady push that goes on for a long time. And to see how we can do that, Chris in the department here has been building this lovely demonstration. And as you can see, this is a go-kart. But it's a rather unusual go-kart because this is powered by a carbon dioxide fire extinguisher. So the fire extinguisher is at the back, and inside the fire extinguisher is carbon dioxide that's been compressed so much that it's turned into a liquid. So there's a lot of carbon dioxide in the fire extinguisher. When I press on the pedal, it will open the valve, and the carbon dioxide will escape with great speed in that direction. And so it should create a force in this direction. So what I'm hoping is that it will push the go-kart forward. So shall we give this a try? Are we ready, Chris? Okay, all set? Okay, here we go. Okay, so that's the principle of the rocket. On the go-kart, we had gases escaping very fast in one direction, providing a force in the opposite direction. But we used a whole cylinder of carbon dioxide just to get a few meters. It wasn't very effective. And the reason is that compressed gas doesn't really contain enough energy. We need some way of getting a lot more energy out of every kilogram of propellant. And to do that, we're going to turn to chemistry. Now, you're all familiar with the motor car, and in the motor car, we take a chemical, a fuel, either petrol or diesel, and we react it chemically with the oxygen of the air. We call that combustion. That produces energy, which drives pistons, which turns the wheels on the car and drives the car forward. Could we use that same principle of combustion to produce not a turning of wheels, but rather a rocket-like force? Well, we can, and the next demonstration, if we could bring this on, please, shows exactly that principle. And again, it's one that's very familiar. It's called the jet engine. So in a jet engine, we burn fuel. In this case, it's a fuel called Jet A1. It's a bit like kerosene, and I have some of the fuel in this bottle. It's reacted chemically with the oxygen of the air to produce an escaping jet of gas traveling very fast, and that produces a force in the opposite direction. So we'll just set this up. And when this is running, it will be quite noisy, so I'm going to wear a pair of ear defenders for this. So this is controlled by a little computer, so I'm just going to switch on the computer. And now we're starting the engine. This will take about 20 seconds or so to start, and it'll run up, first of all, to idle power, which is about 40,000 RPM. And then when it's at idle power, I'm going to ramp it up to full power for just 2 seconds and then switch it off. Why 2 seconds? Well, at full power, it'll be doing 150,000 RPM. It'll generate 100 newtons of thrust. That's 10 kilograms of thrust. The exhaust gas temperature is 700 degrees, traveling at 1,500 kilometers per hour, consuming 1/3 of a litre per minute of fuel and producing 20 kilowatts of power. So here it is ramping up, it's at 18,000 RPM. $25,000 RPM. 35,000 RPM. And it's now at idle power, just over 40,000 RPM. And I'm now going to take it up to full power for 2 seconds. And then I'll shut it down. You ready? Here we go. So that little jet engine is very impressive, but jet engines suffer from one major problem, which is that they require air to work. They need the oxygen from the air. And that's okay in the Earth's atmosphere, but it's no good if we want to go to the moon, because we have to travel in outer space. There's no air and therefore no oxygen in outer space. So we need some kind of propellant which carries its own oxygen. Now, we've met such a propellant already in this lecture. It's gunpowder. Now, gunpowder is really just a mixture of 3 ingredients. So the first one is charcoal. This is powdered charcoal, but it's rather like the sort of thing you might use on your barbecue. So charcoal functions as a fuel. The second ingredient is also a fuel. It's this beautiful yellow element, sulfur. The sulfur also functions as a fuel, and it helps the gunpowder to burn a little bit faster. And then the third ingredient is very important. The third ingredient is called saltpeter, or to give it its chemical name, potassium nitrate. And potassium nitrate is an interesting chemical because it contains locked up inside it oxygen. When it's heated, the oxygen is given off, and the oxygen can react with the charcoal and the sulfur and release energy. Not only does it release energy, it produces a lot of gas. So it produces hot gas with lots of energy, and by ejecting that gas through a small hole called a nozzle in one direction, we can produce a rocket force in the other direction. And if you want to try this, you can buy what are called model rockets. They're on sale in the shops online and in hobby shops. So this is a little model rocket made from a kit. It's essentially a cardboard tube with a balsa wood nose cone and fins. And it's powered by a little gunpowder motor. And this motor, powering this rocket, will take the rocket to 1,500 feet. So it does this by producing lots of gas. Well, we've got an experiment over here to find out how much gas is produced by a rocket motor. So I have a slightly larger motor. And what we're going to do with this motor is to burn it underwater and collect the gas so we can see how much gas is produced. So in this apparatus, we have a tube full of water. We have another one of these motors. It's in a plastic bag so it doesn't get wet, and it's underwater. And when the motor burns, it will produce gas, and the gas will displace the water in this tube, and we'll see just how much gas is produced. Now, to set off this motor, we have an electrical match inside the motor, and it's connected by these wires to the thing which is really my favourite way of setting off explosives, which is this. So this is actually a genuine exploder, as it's called. It's from about the 1920s, and it would have been used to set off dynamite in quarries and mines and that sort of thing. And so we're going to use this to set off that rocket. But to help me, I'd like a volunteer, please. Who would like to come on down? Would you like to come on down? Let's have a big hand for a volunteer. Would you like to come and stand there? What's your name?
Edward.
Edward. Right, Edward, you've seen these on cartoons. Do you know what to do? Okay,
Lift it up and push
exactly.
it down.
You're going to lift it up, and when I tell you, you need to give it a really firm push, as hard as you can. All right? And we're going to watch the rocket burning in that tube over there and see how much gas is produced. Okay, off you go, Edward. And there's the motor burning. And we can see how much gas. So you can see the white gas at the top. All of that gas produced from that one small motor. All right, let's have a big hand for our volunteer. So this gas then is produced by the combustion of gunpowder inside that rocket motor, and that gas is ejected at the back, producing the rocket force going forward. Now, gunpowder is just a mixture of these three ingredients. And lots of rocket propellants, as we'll see in this lecture, are made of mixtures of a fuel with an oxidizing material, such as oxygen. Now, when we're designing a rocket propellant, one of the most important things is to understand the right proportions of fuel and oxidizer. So to see how that works, let's look at this example here, which is the Bunsen burner. Now, a Bunsen burner works by burning methane, or natural gas. So the methane is coming up this tube, it's mixing with the air, and what you're seeing here is a chemical reaction between the methane and the oxygen from the air. So we can ask ourselves, what is the best proportion of methane and oxygen to get the biggest energy release? Well, we can answer this by looking at the chemistry of this chemical reaction. So this is a model of a molecule of methane. So it consists of a carbon atom attached to 4 atoms of hydrogen. Now, when the methane burns, the methane molecules react with oxygen molecules. So here's a molecule of oxygen. It has 2 atoms of oxygen joined by this bond. What happens when the methane burns is the bonds in these 2 molecules break, and the atoms come together in different combinations. In particular, the carbon reacts with oxygen to make carbon dioxide. Now, as the name suggests, carbon dioxide has 1 atom of carbon, 2 atoms of oxygen. So for the carbon to burn, each molecule of methane will need 2 atoms, in other words, 1 molecule of oxygen for complete combustion. So that's the carbon. What about the hydrogen? Well, there are 4 hydrogen atoms, and they can react with oxygen to form water. And the formula for water, as I'm sure you all know, is H2O. That's 2 atoms of hydrogen to each atom of oxygen. So, for the hydrogen to burn completely, we have 4 atoms of hydrogen. They need to react with 2 more atoms of oxygen to make 2 molecules of water. So in total, for every molecule of methane, we need 2 molecules of oxygen. Well, that's our prediction. So let's test that prediction and see if it's correct. So we're going to do that by using these 50 milliliter fizzy drinks bottles as rockets. So in each of these bottles, we have different proportions of oxygen and methane, and we'll fire these rockets, and by seeing how far the rockets go, we can tell how much energy was released. So in the first rocket then, we're going to put lots and lots of methane. The methane is the fuel, so you might think having lots of methane would be a really good idea. So lots of methane, not much oxygen. Okay, I think I travelled about 5 centimetres. All right, maybe not so good. Let's try now having a lot more oxygen. So the second rocket has some methane, but lots and lots of oxygen. So let's see if this can do any better. Oh, not bad, not bad. All right, so let's test our theory then with the third rocket, which has 2 parts of oxygen and 1 part of methane. Let's see how well this does. Okay, so clearly our scientific theory was right. If we have an exact balance between the fuel and the oxidizer, so they're in the correct proportions, we get the biggest energy release and our rocket travels the furthest. What we have there is a mixture then of the fuel, methane, and the oxidizer, oxygen. And gunpowder was also a mixture of fuel and oxidizer. We can actually do a little bit better than just have mixtures. We can actually take a molecule of fuel and actually build oxygen into the molecule. And this was discovered, first of all, by a Swiss-German chemist, Schönbein, and he was working in his kitchen doing a bit of chemistry, sort of as you do, and he had a bit of an accident. He spilled some nitric and sulfuric acid on the bench, or on the kitchen table, I suppose, and he took a cotton cloth and he used the cloth to wipe up the acids, and then he put the cloth on the stove to dry it out. And when it dried out, he made a discovery. He discovered this material. This is called nitrocellulose. So this is just a piece of ordinary cotton cloth. It's been treated with nitric and sulfuric acids, then washed and dried, and it looks exactly the same. It looks just like ordinary cotton cloth, but if I set fire to it, you'll see it behaves rather differently. And you'll notice it seems to have disappeared. Of course, it hasn't disappeared. Matter can't just disappear like that. What actually happened is burned very efficiently. Every molecule of cellulose has extra oxygen built in, so that when it burns, the carbon turns into carbon dioxide, which is a colourless gas. The hydrogen reacts with the oxygen to form water, water vapour, another colourless gas. And there's some nitrogen produced as well, and nitrogen is just another colourless gas that's present in the atmosphere. So it's just turned into colourless gases. In fact, anything that's made of cellulose, which is really plant material, can be treated in this way and turned into nitrocellulose. And so this is just an ordinary sheet of paper which has been treated to turn it into nitrocellulose, and it looks just like paper until I set fire to it. Again, it seems to disappear. So that's nitrocellulose. And we could use nitrocellulose to try to make a rocket. So here's a simple rocket. It's just a tube with some fins and a nose cone, and inside is some nitrocellulose. This time it's actually made from cotton wool. It's actually the sort of cotton wool that you buy in the pharmacy. So again, it's been turned into nitrocellulose, and we'll see if this rocket can fly. Well, our rocket didn't quite reach the moon, but it illustrates the point. And we can use nitrocellulose to illustrate another point as well. This is also nitrocellulose, but this nitrocellulose is in the form of a fine powder. It's called smokeless powder. It's sort of the modern equivalent of gunpowder, effectively, but it contains quite a lot more energy than gunpowder. And I put a few grams of it in a tray, and I'll just light this, and I want you to see how quickly or how slowly it burns. So you see it's burning slowly along the track. It's taking several seconds to get from one end to the other. That's burning just in the open air. But in a rocket, we take our fuel, our propellant, and we confine it in a rocket chamber and allow it to build up pressure. And that build-up of pressure does two things. It increases the rate of combustion, and also the high pressure means the gases come out of the end at high speed, and that gives us extra thrust to our rocket. But we have a problem. If we confine that pressure too much, things can go wrong. And I want to illustrate what can go wrong with the help of another volunteer. Should we have a volunteer from this side? Who wants to come on down? Would you like to come down second row back? Yes, let's have a big hand for our volunteer. And face the audience, what's your name?
Jack.
Jack? All right, Jack. Well, just behind you here in this safety hood, we have another 2 grams of that smokeless powder, but this time it's inside a cardboard tube, and the cardboard tube is bound up with lots of tape, so it's very tightly confined. And again, we have an electrical match inside the tube, so we're going to set off the powder. This time it's very tightly confined. We'll find out what would happen to our rocket if we don't get the design quite right. So if you'd like to come over here. So again, we've connected it up to this exploder. So don't operate that just yet. My prediction is that the rate of burning of that powder will be increased so much that we're going to need ear defenders. So I'm going to give you ear defenders. I'm going to wear ear defenders, and you may wish to cover your ears for this. So this is 2 grams of that smokeless powder, just like we saw in the track, but this time very tightly confined. Okay, off you go. Well done. Thank you very much. Okay, so what we actually got there was an explosion. The effect of confinement was to trap the heat, trap the expanding gases, the pressure builds up, the temperature builds up, and that increases the rate of combustion to such a high level that we actually get an explosion. And that's what can happen to our rockets if the design isn't quite right. So you can see rocket science can be quite tricky sometimes. Now, we've looked at the chemistry of propellants, so we're going to come back later and look again at the chemistry of propellants. But I just want to take a moment to turn and look at the physics of rocketry. And the physics of rocketry also presents us with some very interesting challenges. And to illustrate this, I'm going to need 2 more volunteers, please. I think in the stripy shirt, you were very quick. Yes, on the end, you'd come down. Somebody from over here, you're very keen, so why don't you come on down? And a big hand for our 2 volunteers, please. Right, if you'd like to turn and face the front, what's your name?
Louis.
Louis. And you face the front, stand there, face the front. What's your name?
Albert.
Albert. Right, I've got 2 poles, and they're identical. They have little pegs on the end. And what I want you to do is to balance these. So if you hold out a finger like that, what I want you to do is to balance that on your finger and keep it vertical. Okay, manage that. I want you to do the same thing. That's it. I'll turn your finger the other way up, be easier. I'm going to make it a little bit harder for you, so I'm going to turn it up this way. All right? All right, now concentrate really hard and see if you can keep it upright, okay? Oh, well done. Okay, have another go. Have another go. Try really hard, okay? Got it? Oh, excellent. Fantastic. Thank you both very much. Thank you. So what you saw there was that when we try to balance the stick this way, it's very, very easy. We call this stable. We say this stick is stable. What that means is that if I nudge the stick a little bit, if there's any sort of disturbance, and I nudge the stick, it comes back to where it was. If the stick is displaced, it moves back to where it was before. That's called stable. So that's very easy. When the stick is this way up, however, we call this unstable. Even if I manage to balance this and get it exactly vertical, the tiniest disturbance, as it starts to move, it keeps moving in the same direction. It moves away from where it started. We call that unstable. And the problem we face in rocketry is that all rockets are unstable. If we think about a rocket, imagine this rocket is taking off, it's going up vertically, but there'll be some little imperfection in the rocket, something that isn't quite symmetrical, or a little gust of wind, or something that will nudge the rocket and point it in a different direction. The problem now is that the thrust, the force, is now also pointed in a different direction. So if it starts to deviate, if it starts to change course, the thrust will propel it in the new direction, and it will keep on turning. So if we just fire the rocket, it won't go in a straight line, it'll fly very erratically. And we have to solve that, and we've seen from our volunteer how to solve that. When he was balancing the stick, what he had to do was to keep moving his finger around. Okay? We call that active stabilization. And that's how big rockets work. I think one of the most impressive pieces of engineering of all time is also the largest rocket ever built that's flown successfully. It's the Saturn V. And it took astronauts to the moon in the 1960s. And the Saturn V was an extraordinary piece of engineering. It was the height of a 36-story building. It weighed 3,000 tons, and the first stage burned fuel at the rate of 15 tons a second. So imagine this 36-story building lifting off the ground on 5 columns of flame produced by burning fuel at 15 tons a second, and the whole thing is unstable. So to stabilize it, what they had to do was have these engines, and each engine is the size of a small house, to have these engines swing backwards and forwards and be moved by gigantic hydraulic rams. So as the rocket takes off, as it starts to tilt one way, the engines are pivoted while they're burning 15 tons of fuel a second to correct the trajectory of the rocket. So it's an extraordinary piece of engineering. Now, fortunately, if we want to fly rockets in the Earth's atmosphere, we can do something that's a lot simpler. We can actually make use of the air to provide stability. And I'm going to try to demonstrate this using an experiment which will involve everybody in the lecture theatre. So, hopefully, just before the start of the lecture, you constructed these paper aeroplanes. Now, the aeroplanes are identical except for the location of the paperclip. On the red aeroplane, the paperclip is at the back, whereas on the green aeroplane, the paperclip is in the middle. So if you could all check that whichever colour you have, you've positioned the paperclip in the correct place. Okay, what we're going to do now is the thing that you've always wanted to do, which is to throw paper aeroplanes at the lecturer. So, I'm going to be the target. Your job is to hit me. Now, I'm going to give you a piece of advice that might make it a bit easier. When you throw a paper aeroplane, it doesn't fly horizontally, of course. It descends under gravity. So it's no good throwing them directly at me. What you need to do is to aim above my head. And I suggest you aim for the top of the white screen, and then the aeroplane should descend and reach me. Now, what we're going to do is, first of all, just throw the red darts. So just all the green darts stand down. I'm going to give you a countdown, 3, 2, 1, go. When I say, I want everybody with a red dart to try to hit me. Okay, are you ready? Red darts. Okay, 3, 2, 1, go. Okay, oh. That's cheating. Okay, let's see what happens now if we throw the green dart. So everybody with the green dart, get ready. Okay. 3, 2, 1, go! Okay. Okay, well, as you can see, the darts at the front are all green. For some reason, those green darts flew a lot better than the red darts. The reason is that the green darts are stable, whereas the red darts are unstable. And I can explain why the difference occurs using a little model. So in fact, rather than using a model of an aeroplane, I'll use a model of a rocket. So this is our rocket model. And the first thing we need to understand is a concept called the center of mass. So if I take my rocket and I balance it on my finger, somewhere about there, I think. So the point where it balances is called the center of mass. And we can think of all of the mass of the rocket as acting at that point. And that point acts like a sort of pivot point. When the rocket is in flight, if there's some disturbance that nudges it off course, it tends to pivot around the center of mass. And so I've marked the center of mass on this rocket with this symbol. And so this is the point about which the rocket can pivot. The other idea we need is called the center of pressure. So let's imagine a rocket in flight. We think of the rocket as traveling very fast and the air through which it's flying as being stationary. But imagine you were flying on the rocket. You would think the rocket was stationary and you think the air was coming towards you. We call that the relative wind. So if you're on this rocket, the air is moving towards you, and so there's this wind blowing on the nose of the rocket. Now imagine the rocket is nudged slightly to one side. The wind will act on all parts of the rocket's area, but the overall effect of that is as if the wind was acting in one place. We call that the center of pressure. So roughly speaking, the center of pressure is the place where the area in front is the same as the area behind. So this particular rocket has the center of mass behind the center of pressure. That's a bit like your red rockets, your red aeroplanes. On your red aeroplanes, you had a paper clip at the back, and that moved the center of mass behind the center of pressure. So let's see what happens to an aeroplane or a rocket which has its center of mass too far to the back. So here's our rocket in flight. This is the relative wind as the rocket flies through the air. But if it suffers a small disturbance, it points off in some other direction. Okay? This is unstable. As soon as it starts to change course, it's pointing all over the place. So it's flying very erratically. That's an unstable rocket or an unstable aeroplane. So what we need to do is to change things around a bit so that the center of mass is in front of the center of pressure. And on the paper aeroplanes, we did this by moving the paper clip from the back to the middle. So here's the center of mass, that's the pivot point. The center of pressure is the same because these shapes are the same. So let's see what happens with this rocket. It's flying in this direction, and it's quite happy. If there's a disturbance, it points back towards the direction it was going. So that's why this is stable. Now, we could make our rocket stable by fitting giant paper clips on the front of them. And that would not be a very good idea. We could add lots of lead weight to the nose cone, but that would be very wasteful because in rockets it's very expensive to take mass up into the sky or into space, and that mass is very precious, and we don't want to be carrying empty weight, as it were. So instead we do something different. Instead of moving the center of mass forward, we move the center of pressure backwards. And that's why rockets have fins. The fins are to make the rocket stable. They create lots of surface area towards the back of the rocket, and they shift the center of pressure behind the center of gravity. And so rockets like this are stable as long as they're flying through the Earth's atmosphere. So fins is one way to stabilize a rocket, and there's another way we can stabilize a rocket. And this is very familiar to you. This is a fireworks rocket. So the fireworks rocket doesn't have fins, instead it has this stick, but the effect is the same. The stick creates surface area towards the back of the rocket, and that makes it stable. So if the rocket is flying through the air and suffers a little disturbance, the relative wind acts on the stick and points it back in the direction it's supposed to be going. So that makes it stable. Now, these are the sorts of rockets that you can buy in the shops, but if you go to a professional fireworks display, you will very rarely, if ever, see rockets being used. And the reason that professionals don't like rockets has to do with their stability. So let's imagine the following. Imagine I'm running a big professional fireworks display, and I'm going to launch my fireworks from this spot. And let's imagine that there's a wind blowing. Let's say the wind is blowing from this side, so the wind is blowing across the lecture theatre like this. So I fire my fireworks into the sky, and they explode and make pretty effects. And then the cardboard tubes and the paper, all the bits that the fireworks were made of, they come back down to the ground. And because of the wind, they'll be blown downwind, and they'll land somewhere here. So we'll call that the fallout zone. Now, it's very important that we don't have the fallout zone sitting on the audience. So we'll have the audience upwind, so our audience is here, and the fallout zone is downwind, and everything is happy. What would happen, however, if we included a few rockets in our display? Well, let's think about this. We launch this rocket vertically, but the wind is coming from this side, so it acts on the centre of pressure, and it tips the rocket in the direction of the wind. But the rocket's still burning, so it's now going in this direction, and it's turning the whole time into wind. So rockets are very strange things, because when you launch them, they fly into the wind. So the empty rockets are all going to land here on our audience, and we've created two fallout zones. So professionals don't really like rockets for that reason. So at a professional fireworks display, what you have are not rockets, but these things. These are called shells. This is a relatively large one. This is an 8-inch diameter shell. It's a spherical container of explosives and firework effects. And underneath is a charge of gunpowder. It's called the lifting charge. And this whole thing is lowered into a tube called a mortar, which acts like a cannon pointing straight up. The lifting charge explodes, propels the shell into the sky where it explodes, and all the casing and so on is nicely blown downwind into our fallout zone. So that's what's used in professional fireworks displays. While we're over here on this display, we have some other examples of rockets. We've already seen model rockets. Here's another one. So these are the kinds that you buy in the shops, the little gunpowder motors. But if you get interested in rocketry and you want to start building some bigger rockets, you can. And they're called high-power rockets. And this is an example of a high-power rocket. This particular one has been to 13,000 feet, carrying a lot of electronics on board. And it's powered by this motor. Now, this motor is obviously a lot bigger than the gunpowder motor we saw before, but the propellant is also different. This contains a different oxidizer. It's called ammonium perchlorate. And the fuel is a sort of a rubbery material. It's hydroxyl terminated polybutadiene. And there will be a test at the end, in case you don't remember. So this propellant, so-called ammonium perchlorate composite propellant, is about 3 times as energetic as gunpowder. And so these rockets have very high performance. And the components you see here are for a 6-inch diameter rocket. So these would be assembled into a large rocket, and that would be powered by this motor, again full of ammonium perchlorate composite propellant, very high energy propellant. It's the same propellant as used on the boosters of the space shuttle or on any professional solid fueled rocket. And this motor is pretty much as big as you're going to be able to fly in the UK, simply because the bigger the rocket, the bigger the motor, the more space you need to bring the rocket down safely. And we sort of run out of space on our small island. But if you go to the States, where they have lots of big open deserts, you can fly much, much bigger rockets even than this as an amateur. So we talked there about bringing the rocket down safely. That's tremendously important. And we always bring down the rocket nice and slowly under a parachute. The parachute behind me is the parachute that goes with this large rocket at the back. So we need a way of deploying, of opening that parachute. We also need to decide when to open the parachute. So let's think about a rocket that's taking off. It starts at the ground, and as it takes off, the motor burns, it gets faster and faster and faster, and then the motor runs out of fuel. So it stops burning, but the rocket's travelling very fast at this point, so it carries on climbing, perhaps to several times the height at which the motor burns out. But it's slowing down as it climbs against gravity, and eventually it reaches the highest point, we call that the apogee, and after that it starts to descend under gravity. Now the apogee is the point at which it has the slowest speed. So that's the point where we want to open the parachute, because if we open the parachute when the rocket's travelling fast, the parachute will just be destroyed. So we want a way of opening the parachute at the highest point. And there's one way to do that, which is to use the fact that the pressure of the Earth's atmosphere falls as we go higher and higher. So if we have a system on our rocket that measures the pressure of the atmosphere, it will see the atmosphere at ground level at liftoff. As the rocket climbs, it will measure the atmospheric pressure falling until it reaches the highest point, and then as it starts to descend, the atmospheric pressure will increase again. So by detecting the point at which the atmospheric pressure just starts to increase, we know the rocket is at the highest point, and we can set off our parachute. So, what we're going to do now is have a little demonstration of how that works. And again, I'd like the help of a volunteer, please. Let's have a volunteer. You're very keen. Let's have you. Okay, let's have a big hand for our volunteer. You'd like to come and stand about here. Okay, what's your name?
Amy.
Amy. All right, Amy. What we've got is a bell jar, a sealed bell jar. And inside the bell jar is a little piece of electronics. We call it an altimeter. Just wait there a second. Inside the bell jar, we've got a little piece of electronics called an altimeter, which measures the pressure of the air around it. And in a moment, we're going to reduce the pressure in the bell jar, which represents the rocket climbing. And as we start to increase the pressure again, it should detect that the rocket, if you like, has reached the highest point, and it will deploy the parachute. Now, the way it deploys the parachute is by sending an electrical signal to an explosive charge that blows off the nose cone and ejects the parachute. And we're going to simulate that by connecting our altimeter through wires to a little pyrotechnic device that's sat on top of the fume hood there. So if that goes off, that's equivalent to the parachute being deployed. All right, well, if we'd like to come and just stand here, just swap places, if you stand there, and this syringe is going to allow us to change the pressure in the bell jar. So what I want you to do is get hold of this with your left hand, other hand, that's it. Hold that with your right hand. Then what I want you to do is to pull the plunger this way a few centimetres. That's it, about there. And now push it back in again. There we go. Okay, thank you very much. So that's how we deploy the parachutes on our rocket. Now, we looked earlier at rocket fuels. We looked in particular at gunpowder as a fuel that we can use to propel small model rockets. And we also looked at ammonium perchlorate-based propellants, which are much more powerful, and they're used on large, high-power rockets for amateurs and on large professional rockets as well. Those are both examples of solid fuels. The fuels, the propellants, are in solid form. And they have a really nice advantage, which is that they're very simple. When you set fire to a solid motor, it burns, it does its thing. That's all you need to do, just set fire to it. It also has a disadvantage. Once you've ignited your solid fuel motor, you cannot shut it down. Nor can you control the thrust. It produces whatever thrust it produces, you have no control over that. Often, we want to be able to change the thrust of an engine in flight. For instance, if we're landing on the moon, we need to adjust the throttle of the engine in order to achieve a nice soft landing. Also, if there's a problem in flight, we might want to shut the engine off very quickly. We can't do that with a solid fuel motor. So a lot of large rockets use not solids, but liquids. They use liquid fuels and liquid oxidizers. And these have the advantage that we can control them, we can shut them down quickly, and also they have even more energy than the best solid fuels. So let's have a look at some liquid propellants for rockets. Now, the most common oxidizer for liquid-fueled rockets is just oxygen itself. But oxygen, of course, is a gas. The air in this lecture theatre is about 1/5 oxygen, and it has a very low density. There isn't much oxygen in a given volume. We need to find some way of packing it in so we can fit a lot of oxygen into our rocket. And the way we do that is by cooling down the oxygen. If we cool it down enough to around minus 183 degrees centigrade, it will turn into a liquid. And we can achieve that by using another very cold liquid called liquid nitrogen, which has an even lower boiling point. And we can use that to cool down oxygen gas and turn it into a liquid. And that's what's happening here. So in this cylinder, we have oxygen gas. It's coming out of this tube. It's going through a bath of liquid nitrogen. And the liquid nitrogen is cooling it down so it becomes a liquid. And it's collecting in this vacuum flask. So I thought I'd just show you some liquid nitrogen. So in this box is some hot water, and in this vacuum flask is about 1 litre of liquid nitrogen. So this is extremely cold, and I'll pour the cold liquid nitrogen into the hot water, and we'll see what happens. Okay, so that's got nothing whatever to do with rocket science, by the way. I just couldn't resist including it in the lecture. So in this vacuum flask then, we've made some liquid oxygen. So it's a very compact, very high density form of oxygen. And so it should be a much better oxidizer than just the oxygen in the air. And we can test that with a little experiment. I'm going to set fire to something which ordinarily doesn't burn terribly well, and we'll see if we can speed up its burning. And the thing we're going to use is toast. So I've got a piece of toast. So I'm putting the toast in a tray, and then Chris is going to pass me the liquid oxygen. And I'm pouring liquid oxygen onto the toast. I guess in the spirit of the Science Festival, I'm going to be quite generous with this. So there's our toast, soaked with liquid oxygen. And now we'll set fire to it and see how well it burns in this very concentrated form of oxygen. And it's worth remembering, every time you eat a piece of toast, the amount of energy that's released in your body is exactly the same as the amount of energy that you see being released there. It's just released rather more slowly. So that's liquid oxygen. And liquid oxygen is often used as the oxidizer in liquid-propelled rockets, together with fuels. A common fuel is kerosene, very much like the fuel that powered our jet engine earlier on. Or we may use another very, very cold material, liquid hydrogen. That's hydrogen gas that's been turned into a liquid, again by cooling to very low temperatures. So those are examples of liquid fuels, but there's a special type of liquid fuel that we use under special situations. Let's go back to the 1960s and imagine our astronauts have landed on the moon. They've gone for a moonwalk, they've taken some photographs, they've collected some moon rocks, and the time has come to return back to the Earth. Now, because there isn't very much weight allowance on a spacecraft, they've only got one rocket engine to bring them home. So that rocket engine has to work. It has to be an extremely reliable rocket engine. And the way we can make an extremely reliable rocket engine is to change the chemistry of the propellants. If we choose our propellants very carefully, then we don't need a source of ignition. We call this hypergolic. It means that when we mix the fuel and the oxidizer, they will ignite without any external source of ignition. And that's good if you want to build a very reliable rocket engine, because it means you can do away with all of the ignition systems. You just have a tank of fuel, a tank of oxidizer, and some pipes and valves connecting them to the engine. Now, the actual hypergolic fuels used on the Apollo spacecraft that went to the moon, they used an oxidizer called nitrogen tetroxide, and they used a fuel called hydrazine. Now, nitrogen tetroxide is quite an unpleasant material, but we've got a small quantity in this test tube. It's the brown liquid in the bottom of the test tube. Hydrazine is extremely nasty, and we won't be able to demonstrate that today in the lecture theatre. So we're going to use something a little bit different. It's called aniline, but it has the same property. Aniline combined with nitrogen tetroxide will be hypergolic. I'm just going to put on some safety equipment. I think we'll dim the lights a little bit for this. So we have nitrogen tetroxide in the test tube, and I'm now going to inject some aniline through this syringe. So as you saw there, as soon as you mix the aniline and the nitrogen tetroxide, they ignited, and they're actually quite violent. I think anybody who's sat on the moon and knows that the only way of getting back home is the several tons of hypergolic propellants underneath their feet is certainly a very brave person. So those are hypergolic propellants. They're again examples of liquid fuels. So we've seen solid fuels, which are very good because when you want to use them, you just light them and they just work. There's no further action needed. They're very, very simple. We've seen that liquid fuels are good because you can change the throttle of the engine just by controlling the amount of fuel you inject into the engine, and you can shut the engine down very quickly if you need to. So the question is, can we get the best of both worlds? Can we have a rocket engine which is somehow powered by a combination of a solid and a liquid? And we can. We call this a hybrid rocket motor. And we'll demonstrate a hybrid rocket motor in a moment. First of all, we just need to think a little bit about what we're going to use for the fuel and the oxidizer. So in this cylinder, I have a colourless gas. And the colourless gas has an interesting property, which I'll demonstrate. I'm going to light this splint. And then I'm going to blow out the splint so that it's just glowing and put it into the gas. And you notice the splint relights. I'll do that again. So a glowing splint into the gas, and it relights the splint. Anybody know the name of this gas? Yes?
Purified oxygen.
Oxygen. That's a great answer. Oxygen's a great answer. I'll tell you, this is actually a bit of a trick question, because in school, of course, and you're obviously paying attention in school, you're taught that if you have a colourless gas and it relights a glowing splint, the gas is oxygen. Well, it's a bit of a trick question because this is another colourless gas that will relight a glowing splint. It's not, in fact, oxygen. It's called nitrous oxide, and the common name of this is laughing gas. So if you're unfortunate enough to have an accident, perhaps you've broken a leg or something, and you're being taken to the hospital in an ambulance, and you complain to the ambulance crew that you're in some pain, they might give you a bit of nitrous oxide to breathe because it's an anaesthetic and it will help to numb the pain. We've also seen that it's quite a good oxidizer because it relights that glowing splint. And we're going to show you another demonstration now of nitrous oxide as an oxidizer. And this is actually one of my favourite chemistry demonstrations. It's called the barking dog experiment. So in this glass tube, we have nitrous oxide. So that's going to be our oxidizer. And our fuel is this colourless liquid. It's called carbon disulfide. So I'm going to place some carbon disulfide into the tube. And then Gary is going to shake the tube, and this will allow the carbon dioxide to evaporate. So what we have now is a mixture of carbon disulfide vapour with nitrous oxide. And when we've clamped it back in the stand, I'm going to set fire to this, and we'll see what sort of effect we get. And again, I think we'll dim the lights for this. Chris? So once the lights are down, so that's nitrous oxide. So that's going to be our oxidizer for our hybrid rocket motor. And nitrous oxide has another really nice property. If you compress it, it turns into a liquid. And it does that at room temperature. So we can have liquefied nitrous oxide at room temperature. We don't have to have all the complexity of cooling things down to very low temperatures like we did with liquid oxygen. So nitrous oxide is going to be our oxidizer, and our fuel for this rocket engine is going to be this. It's acrylic, sometimes known as perspex. It's a clear plastic. It's got a hole up the middle, and it's going to burn from the inside outwards. And the nice thing about this is that because it's a clear plastic, we will actually be able to see the combustion happening inside the combustion chamber itself. So we have another piece of the acrylic tube mounted in this rocket engine. At one end we have an injector. That's a hole through which we can inject nitrous oxide. And at the other end we have a graphite nozzle, and that will accelerate the gases coming out of the chamber to very high speed and produce a thrust, not a very big one, but some thrust in that direction. So we're going to connect up the nitrous oxide. I'll switch this on. I'll just purge the engine with nitrous oxide, and I'm going to light it, and I'm just going to do that with a wooden splint. This obviously is just a demonstration engine. On a real engine for flight, it would have a different system of ignition that would ignite it very rapidly, but this is suitable for demonstrations. So what we're doing now is letting a bit of nitrous oxide into the combustion chamber, and it just takes a few moments to get going, but the inside wall of the acrylic tubing is beginning to burn. And once the flame has spread throughout the tube, you see that I can control the rate of combustion by just controlling the rate at which we let nitrous oxide into the combustion chamber. And then if we could just bring the lights down, Gary. Once the lights are down, we'll then take this up to full power. Well, thank you very much. That almost brings us to the end of the lecture. I'd like to thank all of you for coming. Thank you for your attention. And I'm going to finish with one last demonstration of the application of rocket science. Thank you very much.